Hello, students. Today, this is lecture 6, and today we will be moving to chapter number 2, that is known as process management. The process management sometimes we call to be a CPU management also. So, under today's lecture, I will be basically covering the process state diagram and some of the CPU scheduling algorithm. As you all know from our previous session that CPU is one of the resources of the computer system, and we need to learn how operating system manages these resources so that the maximum user task is accomplished within a minimum time frame. So how operating system will try to accomplish this goal by managing the CPU as a resource. So that we will be considering and will be focusing from this lecture. So now we need to think only from the point of view of operating system, how operating system manages the CPU, right? So whenever any program has to be executed, it has to be brought from the secondary storage device into a RAM or a main memory, because RAM is a place or is a device, memory device, where CPU can read or write the instruction directly to or from the random access memory or primary memory, right? So this is the general procedure for execution of any process which is residing in the secondary memory. Okay, I repeat, whenever you want to execute any process which is there into the secondary memory, it has to be first brought into the primary memory, and CPU will read or write instruction directly from the RAM. So that is a general procedure for execution of any process. So whenever you write a C program, say for example sample.c, in which you have got hello world program, and you have saved the program using the name of the file as sample.c, and you try to save it, right? So whenever you save it, it will reside or it will be saved in its secondary storage device. Now whenever you want to execute or whenever you want to compile it, fine, okay, you give the command gcc space sample.c, right? That compile code will again be saved in the secondary. Now when it has to be executed, you give the command dot slash a dot out. Now dot slash a dot out together, dot slash is together known as a execution command, and a dot out is the compiled file that you have got the compiled file and stored in the secondary storage device. So when you give or when you specify dot slash a dot out, so execute a dot out, it indicates it meaning is execute a dot out. So a dot out file will be loaded from the secondary storage device into the primary memory, and then will get executed by the CPU. Now when you give the command dot slash a dot out for executing any of the compiled code, now it may happen that there is no enough amount of memory in the RAM or primary memory. So in that case, the operating system will manage memory in the RAM by swapping out some of the useless process and swapping it some useful process. So this task is also done by the operating system and is known as a memory management. It falls under the memory management technique, right? But here we are here to understand CPU or the process management. So anything that is to be executed has to be first brought to the computer memory so that CPU can be given to it. So a program which is there in the a saved program or the compiled program, a saved program means .c program, or the compiled program a dot out, all those kind of programs are stored in the secondary memory, and as and when you give the command like execution command, it will be brought from the secondary storage device to a primary memory. And when it reaches or when the program is inside the primary memory, at that time we say the program is in the program will now convert it to a process. So that's why process is a program under execution, and it is under the active state, right? It is under the active state. Any program which is residing in the secondary memory is not called to be an active state, it is said to be in a passive state. So a program is a a program is a passive entity and a process is an active entity. Passive entity because it is in the secondary storage device and not under process. And process is a process or program under execution is an active entity because it is there in the primary memory like RAM. Now any process that is there or in the primary memory has some of the information. Okay, so that information is associated with the operating system to identify any process that is currently being executed or currently in the primary memory or RAM. So some of the information, common information, that is there, that is with the process is program counter, stack, data sections, okay, and program sections. And apart from those, there are so many other information which I'll be covering it up in the process control block PCB, right? So at this moment of time, just you need to understand that there are some of the information that is always associated with a particular process, like the process ID, like the process name, the program counter, stack, IO information, etc., etc. There are many information associated with each and every process, with the help of which operating system will identify the process and its information. Now, since we are dealing with right now, we are dealing with the management of the CPU or the management of the process. So we are talking about the management of process which are there at which is existing in the primary memory. So so what is the need of the user from the what is the demand of the user from the process management point of view? The demand of the user from the process management point of view is that how much work done can be done, or what is the quantity of work can be accomplished within a given time frame, within a limited time frame. So what we want is early execution. Okay, as a programmer, what I want is that whenever I give the execution command dot slash a dot, as and when I give it, I need early execution. I need early execution means I want, being a programmer, I want the CPU to be immediately given to me and my program gets executed and I will get the output. That is what the demand of the programmer, and that is what the main task of the operating system from the CPU or the process management point of view. Okay, so basically we are looking for execution of, so in short we are looking for early execution of multiple number of process, okay, which can be executed simultaneously or in a time multiplex fashion. Okay? So maximum throughput I want in a given time frame. So that's why we are trying to understand how the operating system will perform this process management, right? Okay, so if you see any process that is being executed or that is under execution, okay, so if you see any characteristics of the process, then it has some typical characteristics, like for example, uh, suppose there is a process, okay, suppose there is a process P and it has to be executed. Now you give the execution command dot slash a dot out and the program will be brought into the primary memory, and then as and when it reaches the primary memory or allocated in the primary memory, it is not necessary that CPU will be ideal sitting for that process, waiting for that process. So CPU must be busy with some other process. So at that point of time, it will has to wait for some time. But as and when it gets CPU, as and when it gets CPU, it will start executing. Okay, it will start executing means it will execute some of the computation instructions like a plus c equals to a plus b, etc., right? Now after execution of that program for some duration, it may undergo some IO activity may be like input from the user or outputting to the console, like that way. Okay, so doing or before performing any kind of IO activity, it may happen that IO is busy with some other process. Okay, so it has to wait for the other process to complete its IO activity. So any process that is being executed, the common general characteristics of the processes are combinations of different combinations of CPU burst and the IO burst, and it is always general in saying that CPU burst is the initial is the first, it will always be first one to be executed. That is general thing, right? So any process that is being executed is a combination of the CPU burst and the IO burst with the CPU burst at the first one, okay, first cycle. So after that, it may be in any random combination of CPU burst and the IO burst. Now, why I'm saying because CPU burst and IO burst. CPU burst means it uses the CPU as the resource for doing some task, and IO burst, I'm considering during this time frame, it is using some IO resources like printer, monitor, or keyboard, etc. So this is the main characteristics of the any process that is being executed, right? So so keeping this thing in our mind, we'll move to the process state diagram, right? So whenever you want to execute anything, it has to be first brought into the memory, right? So whenever you create any process and you will first store it, you create any process or any program, first you will save the code into the uh, secondary storage device, right? So a compiled code or the .c code will always be there um, in the secondary storage. So whenever a program is residing in the secondary storage device, at that point of time we will say that the process or the program is in the new state, or the process is in the new state. So new state refers to the process and or the program that is residing in the secondary storage device like hard drive. Then after that, when you give the command like /a.out, so the compiled code will be brought from the secondary storage device to the main memory. I repeat, the compiled code whenever you give the command /a.out, so at that time a.out file will be loaded from the secondary storage device into a ready state in a ready queue. So inside every state has a queue. Every state has a queue. Okay, so the a.out file has been put into the ready queue in the ready state. So whenever a program is brought into the main memory, it is not always happen that CPU is immediately given, because CPU may be busy with some other task. So at that time we say that the process is in the ready state. So now when the CPU reaches in the ready queue, okay, when the process reaches in the ready queue, that process will wait for CPU for its turn, right? So because CPU is busy with some other task. Now when the time will come that it has to CPU has to given to the newly arrived process, so then in that case the CPU will be given to the requesting process. So now when the CPU is given to the requesting process, demanding CPU process, that at that time we say that the process is under running state. So whenever a CPU is assigned to any of the process which is waiting in a ready queue, at that time we say that the process is in the running state. Now in the running state, CPU will keep on executing the instruction as written in the a.out file, right? So somewhere in the between of the code of the a.out file, it may ask for some user interactions or any IO activity. Interaction means input from the user through keyboard, or any printing the some file into the on the um, printer, okay, any kind of IO activity, right? So whenever any IO activity is encountered while executing any process, that at that time what will happen is that the process will be shifted to process will be shifted to waiting state. The process will be shifted to waiting state, but it may also happen that it doesn't have any kind of IO activity. So at that point of time, the system will directly go to halt it or stop it. So halt it means the program has been successfully terminated. But it may also happen that during the execution of the process, right? So some IO activity is required. So at that point of time, we cannot keep CPU ideal, okay, waiting for the currently running process to complete its IO activity. So to complete its IO activity, so and to maximize the utilization of CPU, the operating system will shift the currently running process into the waiting process, so that it can perform the IO activity. Now So during IO activity, so it may happen that during IO activity operation, it may happen that the process which is requesting for some IO resources, that resource may be busy with some other process, so it has to wait for the release of that resource so that it can use the resource and complete its task, right? So until the time it will till the time the process who is demanding for a particular type of resource, IO resource, will wait in a waiting queue, being in a waiting state. So any process which is waiting for some IO resources, input output resources, will wait in a being a ready waiting state. So once a time will come that the requesting process has requested some resource and that resource is available. So now when the resource is available, operating system will immediately allocate the process who is waiting in a waiting queue, being in a waiting state. Now then after that, after completing the IO activity by that process, so it may also want to jump directly to running state. So it is not possible to jump from waiting state to running state, because we told you that CPU is always busy. So here, in case of multiprocessing system, what we are trying to do out there is that we are trying to execute the two or more tasks within the same time frame out here. You can see in during this time frame, CPU is busy executing some computation, and here some of the processes are busy executing the IO activity or performing IO activity. So at the same time multiplex fashion, you are trying to perform multi-processing tasks, although with a one single processor. So so that's why it's a example of multi-processing system. So using a time multiplex fashion, you can perform a multi-processing, executing multiple tasks at the same time, although the processor is also only one, right? So now after completion of a waiting state, the process cannot be moved to running state directly, because CPU is always busy with some task. So how it has to execute the remaining tasks? So to do that, the process who have completed for IO activity, who has completed for IO activity, will again moved to ready state, right? So after completing the I activity, the process will be moved to again ready state. So a common or general or a very very common process, what the cycle will be, they will come to ready state, go to the running state. For performing I activity, it will move to waiting state. Again, after completing I activity, it will move to ready state, and then so on. So ready, running, waiting, ready, running, waiting is a cycle that most of the process will perform. Now after completing each and every instruction, okay, as I told already, that the the process will be shifted to halted state, right? So this is all about the process state diagram. There's one more thing about the process state diagram. The situation is, in what situation the process can move from running state to ready state. That topic I will come after some time, right? So now coming to the point, right? Right out here, that there are process, okay, there is a process which is there in the secondary storage device, which will be brought into the main memory by keeping it into the ready queue, being it in a ready state. Then once it gets the CPU, it will switch over to the running state, and in the running state, okay, the CPU will execute the instruction as written in the instruction, the file. Then during the execution, the program might require for IO activity. So at that time, the process will be shifted to waiting state, and it will wait for the IO devices to get free. And when it gets the IO devices, it will complete its execution and again move back to the ready queue. Again, furthermore, CPU will pick the same process from ready queue when its turn will come and complete its execution, being in a running state. So after completing each and every instruction, okay, so the process will be shifted to halted state. Now, very very important thing, okay, uh, that we need to note down in order to understand the very important concept, the maximum throughput. Okay, so a ready queue, in a ready queue, or the ready queue is a place where you keep all set of all different types of job in a ready queue, right? So now there are basically two different kind of job. One is the CPU bound job, and another one is the IO bound job. So from the these two state, running state and waiting state, you have easily understood that in the running state we will try to perform the CPU activity, and in the waiting state you will try to perform the IO activity. So there are two different kind of job: IO bound job and the CPU bound job. In case of the IO bound type of job, right, in case of IO bound type of the process will spend its maximum time for execution in the IO or while performing the IO activity. So say for example, IO bound job, okay, spends 70% of time performing the IO activity, remaining 30% it will try to perform some computation using the CPU. Whereas in case of CPU bound job, the CPU bound job will spend maximum amount of time with the CPU rather than the IO computation, right? So there are two different kind of job: IO bound job and the CPU bound job. Now in order to utilize the CPU efficiently, okay, and to increase the maximum throughput of the system, maximum throughput means maximum work done to be done in the minimum time space, right? So to accomplish this task, okay, the ready queue has to be, in a ready queue there has to be proper mix of IO bound job and the CPU bound job. Now, if you try to keep too much of IO bound job in the ready queue, okay, then what will happen is that CPU will sit idle because most of the processes are of the IO bound job, and they will whenever they will come in the running queue, they will immediately go to the waiting state. So IO resources will be overburdened. Okay, similarly in a ready queue, if you keep too much of CPU bound task and minimal IO bound task, then in that case CPU will be overburdened. CPU will be overburdened, and IO devices will not be utilized efficiently. So while designing the operating system for CPU management task, so we need to always keep in our mind that in a ready queue we have to have a proper proportion of IO bound job and the CPU bound job, so that CPU has always want to execute and all the IO devices are also utilized. So the selection of jobs from the ready queue to from the new state to ready queue is very time consuming and very crucial to increase the performance of the system, right? So keeping this thing in our mind, okay, there are two different kind of scheduler. One is the short-term scheduler, another one is long-term scheduler. Short-term scheduler are responsible for transferring a job from a ready queue to the running queue. So short-term scheduler, as the name suggests, does not spend much of its time for selecting a job from the ready queue and putting it into the running state, right? However, in order to increase the maximum throughput of the system, the long-term scheduler are generally complex because it has to maintain the proper mix of IO bounds up and CPU bounds up in the ready queue, right? So long-term scheduler are complex, okay, as compared to short-term scheduler, and it's also a time consuming because it has to maintain a proportion of IO bound and CPU bound job in the ready queue. So long-term scheduler is a scheduler who is responsible for transferring a job from the new state to the ready state, right? So there are two different kind of scheduler, okay, long-term scheduler and short-term scheduler. If I compare the performance or the complexities of the scheduler, long-term scheduler are generally complex than the short-term scheduler, right? And now coming to the point, scheduler. What is a scheduler? Scheduler is a program who is responsible for selecting a job from one state, okay, or from one queue and putting it into the another queue. And there are two different kinds of scheduler: short term and long term. So this is all about the process state diagram. I have not mentioned the return of running state. At what situation we'll move from running state to ready state. That point again I'm going to commit later on. So we always have to keep it, in our mind that whenever we are performing any kind of CPU management task, we always have to keep in our mind that CPU has to be busy all the time because CPU time is very precious. So with the help of this architecture, um, that is process state diagram. Using time multiplex fashion, we can keep CPU always busy with at least one job in hand to execute, right? So with this we can, I think we can move ahead with the remaining topic, right? So now whenever I transfer a job from the new state to ready state, I admit it from the new state to ready state, from into the ready queue, right? So now from the ready state, okay, short-term scheduler, with the help of scheduler dispatch, transfer a job from ready queue to running queue, changing the state of the process from ready state to running state. Now, after execution, if all the instructions are executed, then the scheduler, then the process will be shifted to halted state. If it requires high activity, so then it will be shifted to waiting state, and then so on, as I've told you already, right? Okay, fine. Now, so as the name suggests, we have seen already process state diagram. Okay, these are the various states of the process state diagram: new, ready, running, waiting, and terminate. Okay, there are some other name given to the terminate: halted state and exit state. You can use any one of them. Okay, so the detailed instruction I have already explained. You can go through the notes. Okay, now now there are we will talk about CPU scheduling algorithm, some of the examples of CPU scheduling algorithm. So basically we are talking about, short-term scheduler, right? We are basically talking about short-term scheduler or the CPU scheduler. Okay, so there are various different kind of short-term scheduler or CPU scheduler, because in case of CPU scheduler, we are trying to understand when I should give CPU to the process, as the diagram suggests. Okay, from changing any process from ready state to running state means that when should I give CPU to a process. So that is what we are trying to understand with the help of this scheduling algorithm. So some of the scheduling algorithm we have already seen it, although I will be um, doing a revision on the same, right? So some of the very common CPU scheduling algorithms are FCFS, SJF, right? FCFS stands for first come first serve. SJF stands for shortest job first, right? There are two versions of shortest job for that I would be explicitly covering up in today's session. Next is the priority CPU scheduling algorithm, and next one is the round robin, right? Nowadays, in advanced operating system, or the modern operating system, not only uses a single CPU scheduling algorithm, they use hybrid, a mix of those. Okay, so which can you can explore on your own later on. Before I talk about the various CPU scheduling algorithm, I would like to give some terminology. Okay, use some terminology which you should be aware of it and friendly with it, right? Waiting time. So we have to understand what is the meaning of waiting time and what is the meaning of turnaround time, right? Suppose at time ti there is a process, okay, that has reached the system. Okay, now at time to, okay, at time to, it has the process is given the CPU, right? The process is given the CPU at time to, okay, because when the process has reached the ready state at time ti, CPU might be busy with some other process, so it has to wait. So it has waited from ti to to, right? So from at time to, CPU was given to that requesting process, and CPU has started executing the CPU burst of that requesting process from starting from T0 to 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 TP. So from TO to TP is the CPU burst time or the burst time for the requesting process. So the amount of time the requesting process waited is TO minus TI. So TO, the time elapsed between TO and TI. Okay, TO minus TI is known as waiting time, and the turnaround time is TO to TI plus the time elapsed between TP to TO. Okay, so that is known as the total time. Job was submitted at TI, and job was completed, and the process was completed at TP. So the TP minus TI is also known as a turnaround time, right? So that's why, as the name suggests, turnaround time is the time elapsed between job submission to job completion, right? So waiting time plus execution time. As I told you already that execution time I can use sometimes the another word, a nomenclature, burst time also. So now we will look into the various CPU scheduling algorithm. I'll just quickly go through it because we have already covered it. In case of first come first serve algorithm, we will give the CPU to that process which have arrived at the system first. Okay, let us consider there are four processes which have arrived at the system at time t equal to 0 in this order, given order, arrow order. Okay, so J1 have come first, J2, J3, J4, although they have arrived at the system at the same time T0. Okay, so it is very very obvious that since J1 have arrived first, so J1 will be given the first preference to the for allocation of CPU to it. So J1 will be executed for 15 units of burst time. J2 will be executed for 8 units of burst time. J3 will execute for 10 units of burst time, and J4 will execute for 3 units of burst time. So with this we can calculate the waiting time of each and every process. Now I'll be like only one example I'd like to explain it regarding the waiting time, right? So J1 have not waited for any time because as and when J1 was given, assuming that CPU was free at the time when J1 have arrived at the system, so J1 have been immediately given to the CPU, right? So but during the execution of this J1 for 15 units, J2 also have arrived at the same time that J1 have came. Okay, time t equals to 0. So J2 have to wait for J1 to complete. So J1 burst time is 15. So J2 will wait for 15 units of time. So that's for J2. Similarly, you can easily identify the waiting time for J3 and J4. So if I average all the waiting time of this various process, so I'll get the average waiting time as 17.5. Now next scheduling algorithm that I'll be talking about is the shortage of scheduling algorithm. In this algorithm, considering the same scenario, considering the same situation, I will give the CPU to that process having the minimum burst time, right? Having the minimum execution time. So for example, we have the same scenario. All the processes have arrived at the system in this order at same time t equal to 0. So now CPU will be given to that process, okay, or that job having the minimum burst time. So J1 is having 15 units, J1 requirement is 15 units, J2 requirement is 8 units, J3 requirement is 10 units, and J4 requirement is 3 units. So out of these four, J4 is will be given the CPU because it has got minimum CPU requirement time or the burst time, right? So J4 will be given first, right? Then when J4 was executing, J1, J2, and J3 has to wait. Okay, J2 has waited for some time and has and will get the CPU and will start executing. Similarly, J3 and J4, sorry, J1. Okay, so now we have already seen how to calculate the waiting time for each and every process, and 8.75 is the average waiting time for this using scheduling algorithm. I repeat, we have already covered the first two, okay, FCFS and SJF. So that's why I'm quickly doing a revision on it. So if I compare the average waiting time, that is 8.75 using SJF and FCFS with 17.5, so we can easily say that yeah, uh, SJF performance is better than SJF. Shortage of force performance is better than FCFS because it has got less average waiting time as compared to FCFS, right? So as a user demand, I want the program to be for early execution. So all this process will execute early. Okay, if I adopt if the user or if the operating system will adopt shortage of first. So right now I'm just comparing the SJF and FCFS. Okay, we will see some more algorithm later on, right? So the if I just simply compare FCFS and SJF, okay, so the performance shown by the SJF seems to be better one because the average waiting time is less in case of SJF as compared to FCFS, which is 17 approximately 17 milliseconds, 17 units is the average waiting time in FCFS, whereas in case of SJF it's 8.75. So that's why we say that SJF performance is better. Now, talking about the classification of scheduling algorithm, there are two different classification of the scheduling algorithm: non-preemptive and preemptive. Non-preemptive means once the operating system assign CPU to particular process, the process will not release the the process will not release the CPU voluntarily. Okay, I repeat, in case of non-preemptive, once operating system assigns CPU to a process, the process will not release CPU voluntarily until and unless it completes its task entirely. Suppose a CPU is allocated to a particular process with 3 units of burst time. So until 3 units have completed, okay, the process will not release CPU. That is an example of non-preemptive. Whereas in case of preemptive, what will happen is that once the operating system will assign the CPU to a particular process, during the execution of the process, in between, right, in between, during the execution of process, there may be an interruption. There may be an interruption that the currently execution process from the currently execution process, CPU might be snatched and given to some another process, right? So we will see that example with the help of the SJF preemptive. So SJF preemptive, so SJF has two versions, okay, non-preemptive and preemptive. Okay, so we will understand preemptive SJF with the help of the example. Suppose we have got four process, okay, J1 with 15 units, J2 8, J3 10, and J4 3. Okay, and all those have arrived at the same time. Okay, in the order. So, according to the strategy of the CPU scheduling algorithm that follows the SJF strategy, so J4 has to be given for 3 units of time, right? J4 has to be given for 3 units of time. So yeah, the CPU will be assigned to J4. Okay, now for the first unit, okay, as shown in the diagram, for the first time, red color is the completed one. Okay, 1 unit out of these three, 1 unit CPU has executed completely, right? So J4 remaining J4 time is now 2, right? Remaining J4 time is now 2. Now again, at time t, this time at this time when J4 1 unit was completed, J5 have arrived with one burst time, right? So in a system pool, okay, J1 J2 J3 and J4 and J5 are there at this time. So at this time when J4 have completed for 1 unit of J4, okay, J5 have came, right? So at that time 15 8 10 2 and 1 are there. Okay, now at that point of time, what will happen in case of SJ preemptive? At that point of time, what will happen is that CPU will be snatched from the J4 and will be given to J5, just because the remaining burst time for J4 to get completely executed is 2, whereas J5 is 1. So the CPU requirement for J5 is less than the J4, right? So that's why CPU will be snatched from the J4 and will be given to J5, right? Okay, so this is the basic strategy of the preemptive scheduling algorithm, right? I hope I had made it clear. In case of preemptive scheduling algorithm, any preemptive scheduling algorithm, at a particular each and every interval of a time, the scheduler will check if there is any process that is satisfying the criteria. If it is satisfying some criteria, then the CPU will be snatched from the currently executing process and will be given to the new process who is satisfying the criteria, right? Similarly, at this, after completing J5, which requires only 1 unit of CPU time, after completing J5, okay, we have got remaining time, remaining job J4 J3 J4 J3 J2 and J1, okay, with 2 10 8 and 15 respectively. So out of this, again J4 will get chance, and then this is how it will work. Now we will talk about SJ preemptive. Okay, in case SJ preemptive follows shortest job first. Okay, in case of preemptive, what will happen is that whenever at each equal interval, whenever it satisfies some criteria, CPU will be snatched and will be given to another process, right? So here at every interval, what we are going to do out here is that from the pool of job, we will try to find the that job with the minimum burst time, right? So that's why SJF preemptive is also known as shortest remaining time first scheduling algorithm. I repeat, SJF preemptive is also known as shortest remaining time first scheduling algorithm, because at this time, okay, whenever J5 have completed, we have again given the CPU to J4, because remaining time for J4 to complete was 2 and was minimum among the list of job. So that's why shortest remaining time first scheduling algorithm is the another name for shortest job first of preemptive version, right? So this is all about the SJF preemptive. The proper example I have not done, you can do based on our previous discussion, right? So now next scheduling algorithm is the priority scheduling algorithm. We all know that in a computer system, okay, in a ready queue, there are a lot of processes with the different priority. Each one have own priority. For your kind information, you know that CD-ROM has the highest priority. Okay, it's just example. So every process has a a priority associated with value. Okay. Now in this example, let us consider there are four jobs with the burst time and the priority, right? So I am giving one as a priority to that process. One means one is numerical value. Okay, numerical value one means higher priority value. Two is next higher, like that way, right? So the hierarchy is maintained 1, 2, 3, 4, like that way. The priority hierarchy, right? So this is the current snapshot of the system. So J4 is having the highest priority. Okay, J4 is having the highest priority. It's only one priority, first priority, right? With the 3 burst time. Okay, now J4 will execute for 3 units, and then followed by J2. Why J2 will execute after J4? Because J2 is in the next hierarchy from the priority level point of view. And I'm giving the example from non-preemptive scheduling, non-preemptive category of priority scheduling algorithm, right? So this is how it will work. So J4, J3, J4, J2, J3, and J4 is the sequence of job that will be executed considering the priority, right? Now you may consider the priority scheduling algorithm as a special type of shortest remaining time first scheduling algorithm, because here you are trying to, in priority scheduling algorithm, you are trying to assign a CPU to that job which is having a high priority in a priority hierarchy level, right? So whereas in case of the shortest remaining time or SF algorithm, we are trying to give the CPU to that process having the minimum burst time. So you can consider a relation something similar to this, right? You can consider some relation something similar to this. Priority is inversely proportional to the burst time. So the lower the burst time, higher will be priority, right? You can consider that way. So let us come back to the priority scheduling algorithm. So J4 have started execution at time t equal to 0, and J2 have started its execution when J4 have completed. J3 have started its execution for 10 units when J4 and J2 both have completed, and has waited for 11 units of time. Okay, that is 8 plus 3. Now J1 have completed or started its execution from time 3 plus 8, that is 11 plus 10, that is 21. So J1 I have waited for 21 units of time, right? So average waiting time is 8.75. Okay, so this is all about the priority scheduling algorithm. I repeat, the priority scheduling algorithm is a special case of a special type of a shortage of first, in which the relation is the process with the least burst time will be given the maximum priority. So that's kind of a relationship, right? Okay, now um, the SJF and priority scheduling algorithm falls under the same category. Okay, based on our discussion. Now talking about the problems. Okay, the problem of the priority scheduling algorithm is that the process which is having a minimum priority, right? The process which is having a minimum priority will never ever get a chance will never ever get a chance, because if you see the snapshot of the system, this snapshot of the system is taken at time t equal to 0. Suppose at time t equals to 1, another jobs come. At time t equals to another job so every time a new job is coming with some different priority, so there must be some process who is waiting from initially beginning and have the minimum priority. Such kind of process will never ever get a chance of CPU. So that kind of problem is known as aging. Aging, as a layman term, aging, it gets age, right? And as per the time, as per the like time span, okay, as and when time progresses, the age of the person is increasing. Okay, so similarly, that indeed the word has been associated with that word called aging, right? So the job with least priority will never get chance to execute. Okay, so what could be the solution for this kind of problem? So solution is the like increasing the priority. So as and when the time progresses, because CPU is busy executing some other task, and the process with the minimum priority should gain the priority. Okay, at time t equal to 0, suppose the priority was x. Okay, now it should be, after some time, it should be x minus y, where x minus y is having the um, meaning is priority with at a higher hierarchy, right? So if you follow this kind of strategy, it is definitely that at some point of time later on in the future, a process will definitely have a highest priority and will get a chance to execute, right? So this is all about today's sessions. I hope you had liked it. Just to summarize you, what we have discussed was, okay, so we have discussed the various CPU scheduling algorithm, and we have discussed the process state diagram. Okay, now I would like to, before terminating the today's session, a small topic that I would like to cover, which I have escaped. Okay, so during the execution of the any process, due to, say for example, preemptive SAM. Okay, maybe there was some process with the minimum remaining burst time. So to that process, it has to give CPU. So suppose the process P1 is running at time stamp 10 unit of time, right? So at time 10, P1 was running, right? Now at time T12, okay, P1 was exited from the running state, because there was another process P2 with renaming burst time as minimum, right? Okay, so this may be a situation. Okay, so in that kind of situation, sometimes the process might be shifted from the running state to the ready state. So an interrupt will be generated, with the help of which the shifting of process. Okay, the shifting of process from running state to ready state will directly go in this direction. Okay, that's all for today. I hope you have understood the topic. If there is any questions, please definitely raise the question in the post section, or you can discuss in our discussion section, right? If there's any questions, please definitely post it, right? Thank you so much.